let's kick it off, our track. So our first speaker will be Germán, all the way from Buenos Aires. So he'll be talking about his work on SciML, specifically on the model called GOKU-UI. And yeah, let's hear what Germán has to say, and let's give him a round of applause. Our first speaker, good luck.
Thank you very much. Okay. Well, hi everyone. My name is Germán Abrevaya. I am a physics PhD student from University of Buenos Aires. And today I will show you an example of how we started with a given SciML model and improve it to the point to be able to handle one of the most complex systems in the world, which is the brain. So, as you know, this work is in the context of SciML, and in particular, we've been working with latent differential equation models, which you can think of as some kind of variational autoencoder with differential equations inside ruling the latent space dynamics. Specifically, we work with a model called GOKU-nets, which, as in any autoencoder, the goal is that the output reconstructs the input as close as possible. And in this case, the inputs are high-dimensional time series. Initially, each time frame is processed independently, usually reducing the dimensionality. Then they are processed sequentially for learning the parameters and initial conditions of a differential equation, which is explicitly provided, allowing you to incorporate some prior knowledge about your system. Then the equations are solved, and lastly, the trajectories are transformed back to the original space. So as I told you, we wanted to apply this to neuroimages. And we use resting state fMRI, and for the differential equations, we use some Stewart-Landau oscillators, which is a well-established model for neural ensemble dynamics. The issue with these models, and in general with differential modeling, is that for training them, you have to differentiate through the solver, calculate gradients with respect to the initial conditions and parameters, which tends to produce a quite complex loss landscape. And in turn, this can make the training a bit challenging. So it is well known that even if you have very simple oscillatory data, training a neural ODE on this data can be stagnated on this kind of local minima. One possible solution is to use a multiple shooting training strategy, which consists on splitting your time span in multiple shorter windows and impose some continuity constraint between the windows. This was already implemented for neural ODEs. Actually, these animations are from the defect flags documentation, but we extended it for latent differential equation models where you don't have access to the ground truth initial conditions for each window because the differential equations are happening in the latent space. But you can still try to impose the continuity constraint. So we developed a multiple shooting training strategy in the latent space using multiple initial conditions, but the single shared set of parameters for all windows, and added a regularization term in the loss function. In addition, we added an attention mechanism to the part of the model that learns the parameters, which originally was this bidirectional LSTM. So to the GOKU-nets, with all of these enhancements, we call it GOKU with ubiquitous inference, or in short, GOKU-UI. So now let's see in detail all of these enhancements. Let's start by recalling how a traditional bidirectional LSTM works. So you have your time series, and you have one LSTM processing it forward in time, another LSTM processing it backwards, and the final output is the concatenation of the last output from each LSTM. On the other hand, on our attentional by LSTM, you keep all the outputs from both LSTMs and do a linear combination of them weighted by some attentional scores. So now let's see a toy example of the multiple shooting. So you split your time series into multiple overlapping windows, and then you have one LSTM processing all the windows. And eventually, their outputs will end up being the initial conditions for the different multiple shooting windows. And then by using the parameters that are before, you integrate all of them in parallel and add a regularization term in the loss function, quadratically penalizing for the differences between the initial point of each window and the last point of the previous one. We evaluated this on two datasets, one synthetic and one empirical. For the synthetic one, we use 3 coupled stochastic Stewart-Landau oscillators and enlarged the dimensionality so that we had some high-dimensional inputs for the model, which were actually sourced from known low-dimensional dynamical system. For the empirical data, we use resting state fMRI, the time courses of an ICA analysis, and inside the GOKU-nets, we use 20 Stewart-Landau oscillators. We evaluated this on the reconstruction task, but also on forecast task, because for all of these models, you can continue integrating the equation further in time beyond the reconstruction limit in order to have some forecast of the future activity, and compare them against a few baselines. So let's see some results. Here you have the result for simulated data. These are the reconstruction error on the left and the forecast error on the right in function of the size of the training dataset. And keep in mind that all the axes are in logarithmic scale. So we can see here that already adding the attention mechanism, which corresponds to this orange line, the reconstruction improves with respect to the plain GOKU-net in turquoise. If you trained with multiple shooting, this green line, it improves even further. But the best overall performance is achieved by GOKU-UI, which is a combination of both mechanisms, which is this purple line, and which achieves a threefold reduction in reconstruction error compared to the plain GOKU-net. And also it displays a very good data efficiency, achieving its peak performance with only 300 training samples, surpassing other models which were trained with up to 16 times more data. On the forecast task, we see that for very little training data, the VAR, the vector autoregressive model, surpasses all the other models, which is expected because in general, statistical models are expected to surpass machine learning models when you have very little data. But if you have more data in your training data set, then you get some similar results similar trends than in the reconstruction. These are some examples of the reconstructions on the test set. And here we see that the reconstruction from GOKU-UI are much closer to the ground truth than the plain GOKU-net. On the empirical data, we see, again, we have reconstruction on the left, forecast on the right, and we see that in this case, the attention mechanism didn't improve much the results, but the multiple shooting did, and very significantly. And actually, GOKU-UI achieved a 5-fold reduction in reconstruction error compared to the plain GOKU-net. And on the forecast side, again, the VAR got the best result for the very beginning of the forecast, but its performance decreased very rapidly, and then GOKU-UI take the lead and get the best performance, best forecast performance up to 15 seconds ahead. And lastly, also these are some examples of reconstructions from test subjects, and we can see that again the reconstruction from GOKU-UI are much closer to the ground truth than the plain GOKU-net. So, in summary, we significantly enhance the GOKU-nets, or you could say that we increase GOKU's key by adding some attention mechanism to the part of the model that learns the parameters, and develop a multiple shooting training strategy in the latent space, using multiple initial conditions, but a single shared set of parameters for all windows. And the regularization in the loss function, penalizing for the discontinuities in the latent space. And by doing this, we increase the performance and data efficiency on both reconstruction and forecast tasks on simulated and empirical dataset. And moreover, we were able to encode the whole brain dynamics into a latent, low-dimensional, and interpretable dynamical system, which we will try to leverage for getting some neuroscience insights, such as functional connectivity or doing some classification on mental states or conditions. Well, this is all the amazing people who contributed to this work. And you can scan this QR for getting access to the full paper, the codes, and also for a specific ChatGPT instance that is expert on our work and will hopefully be able to answer all of your questions. Thank you very much.
Yeah, are there any questions for Germán? No questions from the audience? Yeah, then I'll have just one question. We have time exactly for one question. So you've experimented with the brain scans, right?
Yes.
Like then where do you see it can be applied, like, also besides like brain scans? Did you think about it? Like, are there any?
Yeah, it is like a very general machine learning architecture.
Yeah.
So, and you can change the differential equation for any other type of equation. Actually, that is one of the advantage that the GOKU-nets were originally in Python, and just by coding it in Julia, we can leverage all the power of the SciML ecosystem, and you can use any kind of differential equations. So if you have your particular system of interest, you can try to guess some underlying equation that rule the dynamics, and even combine it with neural network terms, such as like in the case of universal differential equations, but inside an autoencoder, which learns the.
Awesome. Yeah, great work. Let's give
Thank you.
a round of applause to Germán.
Thank you very much.